Okay, folks, we're going to continue on. We're going to do a little review now of polar coordinates. So let's see what we got. So the idea with polar coordinates is that instead of obtaining a point on in the Cartesian coordinate system using, well, Cartesian coordinates, just simple left, right, up, down movements. Instead, if we had a point out here, let's say at this point we call it, I don't know, x, y. There's another way of representing this point. Notice that this point has a certain distance from the positive x-axis. It also makes a certain angle with the positive x-axis. And so you might recall that we call that distance r, and we call that angle theta. And so just like we could label a point with x, y, in other words, how far from the origin, left, right, and up, down is it, we could just as easily identify a point by how far from the origin is it, and what angle does it make with the positive x-axis. And so that's what essentially polar coordinates do. But notice a few things. First thing to notice is that this distance down here is x, and this distance here is y. And so we have a simple Pythagorean theorem, right? X squared plus y squared equals r squared. And what about the angle theta? Well, let's think about what x is, right? We could say that x is, well, r cosine theta, because after all, right, cosine is adjacent x over hypotenuse r. Y, well, opposite over hypotenuse. So y is r sine theta. And then the other thing to notice is that tangent theta, well, tangent is opposite over adjacent, right? So tangent is just y over x. And so we have a way now of translating between the two coordinate systems, okay? So let's see how that works. And again, this should ring a bell, but let's plot some points here. So 2 pi thirds. How does this work? Well, the radius is 2. So, and just to let you guys know, these dark lines are, dark curves are units. So 1, 2, and then pi thirds. I want to rotate pi thirds. Well, just to let you know, let's see here. This is pi fourths, pi sixths. And so let's see. Actually, what does this go by? Here's our pi thirds here. What's going on here is we're going by pi twelfths. So this angle here would be pi sixths, pi fourths, and then pi thirds. So that point is the point 2 pi thirds. And notice what we've done. We've started at 2, and where, if you think about it, you could picture this as having rotated this radius of length 2 on the x-axis in the positive direction, pi thirds, okay? Now, what about b? So b, we've got 1 negative pi fourths. Well, negative, right? Remember that when you're rotating, the positive direction is counterclockwise, and the negative direction is clockwise. So I'm going to come over here to 1, and I'm going to rotate in the negative direction, pi fourths. And so that point there is 1. Oops, no, it's not. I need to go 1 more. Right here is the point 1 negative pi fourths. Okay. How about C? Why don't you guys try C? Pause it and give it a try. Come on, pause it. All right, so here's 2, and I'm going to rotate 7 pi sixths. So here's 2, and I'm going to rotate all the way, right, from here all the way to here. That's pi, so that's 6 pi sixths. I'm going to go 1 more pi sixth for 7 pi sixths. So right there. That's the point 2, 7 pi sixths. All right. And then how about the last one, a negative 2? Well, negative 2, a negative radius means you start over here, right? And then we're going to still rotate in the positive direction, 2 pi thirds. So again, that's pi sixths, that's a pi fourths, that's a pi thirds. So 1 pi third, and then we're going to go 2 pi thirds, okay? So negative 2 pi thirds. And it's worth noting that that's the same as if I had started at 2 and gone down negative pi thirds, right? That identifies the same point. In fact, I could even say that those are equal. It's the same as 2 negative pi thirds. So there's all sorts of expressions for the same points. They're not necessarily unique, but this is how you graph. So hopefully this is ringing a bell. Let's keep going. Convert from rectangular to polar coordinates. Okay, so 4, negative 4. So that's going to be the point down here, right? Call that 4, negative 4, because that would be 4, and that would be negative 4. There's my radius. And if I want, do a positive theta, there's my theta, okay? Well, let's look at the radius. X squared plus y squared equals r squared. So we're going to get 4 squared plus 4 squared equals r squared. And so 32 is equal to r squared. So our radius is going to be 4 square root of 2. Okay? And now theta, well, let's see here. Tangent theta equals, well, y over x, right? So negative 4 over 4, which is negative 1. Well, where does tangent equal negative 1? Well, if you're looking at inverse tangent, right, that would give us an angle of negative pi fourths. Or if we want to measure in the positive direction, recognizing that we are in quadrant 4, then that would be what? Well, 1 pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths, 5 pi fourths, 6 pi fourths, 7 pi fourths, right? In other words, just pi fourths short of 2 pi. And so you could write that point as 4 root 2, and then take your pick, either one of those. I'll use the positive one just because in times like these, it's good to stay positive. All right, how about the next one? Negative 2 root 3. Well, let's see. We're in quadrant 2, and so I'm just going to kind of eyeball this a little bit. Sure, why not? Negative 2 root 3. So that point is negative, or that x coordinate is negative 2, that y coordinate is 4. Well, just like before, right, my r squared is going to be x squared plus y squared. So what do I get, 13? No, I don't. I'm sorry. What am I doing? I get 4 plus 3, which is 7. So r is the square root of 7. And then my angle, well, tangent theta, y over x, so 4 over -2, which equals -2. And so where's that going to happen, right? I mean, really, you could think of that -2, if you want to think back to your trig, as -2 over √3 and 1 over √3, right? And so where would that be? And so you get theta is approximately 2.03. And again, that's radians. So our point here is √7, 2.03. All righty. How about part C here? So -7, 0. So we're on the x-axis, negative x-axis. And let's think about what this means. If I start with a positive radius, then that distance is 7. And then how far will I have rotated if I go to there? Well, that's right, pi. Okay? All right. Let's go the other way as well, right? Convert from polar to rectangular. So we have 3 and 11 pi sixths. So let's think about where that is, right? 3 and 11 pi. You know what? Let me draw a little better axis there. You know what I'm going to do? I'm actually going to do this. Let's see. Let's do this right here. Okay, so 3, 11 pi sixths. Well, 11 pi sixths is going to be just shy of 2 pi, right? And so we've got this distance, which is 3. And I want my x and my y. Well, x is our cosine theta. So 3 cosine 11 pi sixths, which is going to be 3 times √3 over 2, which we could call 3 √3 over 2. And then y is just our sine theta. So 3 sine 11 pi sixths. And again, we're in quadrant 4 there. So sine 11 pi sixths is going to be -1/2. So we have -3/2. So in Cartesian coordinates or rectangular coordinates, that point is 3 √3 over 2, -3/2. Okay? How about the next one? -1 pi. Well, let me give us another axis here. Uh-oh. That's not what I wanted. Sorry, guys. Actually, let's... All right. So -1 pi. So -1 is going to be over here. And we will have rotated, right, pi radians. Well, gosh, that's just -1, 0, right? If you want, you're more than welcome to say, okay, well, x equals radius, which is 1 cosine pi, and y equals 1 sine pi, but, don't miss the obvious here. Right, that'll be 1 times -1, that'll be 1 times 0. So in Cartesian coordinates, it's -1, 0. But again, be careful here. You don't want to look at this -1, 0 and say, oh, it's the same as this -1, 0. No, no, no. Because in this -1, 0, we're saying we have a radius, -1, and radians measure of 0. okay? That's an angle, not an x and a y. It's a distance and an angle. So when we talk about, when we convert to Cartesian coordinates, yeah, the numbers are the same, but we're talking about an x and a y, all right? How about one more? So let's just kind of trust the math here, right? We could just as easily say, okay, well, x is r cosine theta and not worry about drawing this thing out. So negative 15 pi fourths, which will be, and be careful here, right? Negative 15 pi fourths, after I just said we're not going to draw it out, right? We're going in this direction. And then that's multiple times around the circle, right? So if you think about this being 16 pi fourths, that's the same as 4 pi, which is 2 laps. Well, we're 15 pi fourths, which means we'll be just pi fourths shy of 2 laps around this circle. So this is actually the same as 5 cosine pi fourths, which will be 5 times root 2 over 2, okay? And similarly with y, will be sine negative 15 pi fourths. But we all know, like we just said, that's 5 sine of pi fourths. And so we get, again, 5 root 2 over 2. So my Cartesian coordinates are 5 root 2 over 2, 5 root 2 over 2. Hopefully this is ringing a bell. Let's keep going. So rectangular to polar equations this time. So x squared plus y squared equals 49. Well, we know that x squared plus y squared is r squared. So this is just r squared equals 49, which is just r equals, if we want our r's to be positive, 7. Oh, well, think about this. We know that x squared plus y squared equals 49 is a circle, and a circle has a constant radius, right? And what do you know? R equals 7, constant radius, okay? How about x equals 4? Well, we also know that x is equal to r cosine theta. So we have r cosine theta equals 4, which means if I think of r as a function of theta, then I have r equals 4 over cosine theta. Or if I wanted to, I could call that what? 4 secant theta. Okay? All right. How about c? So when you look at c here, I'm going to rearrange this, right? X squared plus y squared minus 4x equals 5. Well, x squared plus y squared, we know that that's r squared. And we know that x is r cosine theta. Okay? And so I could write this. All right, how about the other way? Polar to rectangular. Well, if r is equal to 3, r squared is 9. And why would I want to have r squared instead of r? Well, it's simple. I know the conversion. I know that r squared is x squared plus y squared. Okay? Then how about b? R equals 3 cosine theta. Well, I'm going to start with this r equals 3 cosine theta. And what I'm going to do is I'm going to multiply both sides by r. And the reason I'm doing that is because, well, 2 reasons. One, r squared gives me an x squared plus y squared. And then r cosine theta I know is x. Okay? So I have x squared plus y squared equals 3x. Okay. Now, it's worth noting that often which form we use should be dictated by ease, right? If we're writing, sometimes equations are just simpler in polar form, like a circle. R equals a constant. That's a very clean equation, as opposed to x squared plus y squared equals 4. In fact, or r squared rather. That's not even a function, right? X squared plus y squared. So sometimes polar coordinates are just nicer. All right. So the next issue that we want to look at, and I'm going to put that in our next lecture, is getting our hands on the curves that we might see in polar coordinates. There are some curves I want you to be able to recognize, and we're going to go over what those are and what those forms are. I'm going to use Desmos quite a bit, and so spend some time getting used to polar coordinates and going from one Cartesian coordinates to polar and vice versa, as well as translating the equations back and forth, and then we'll start getting into some curves. Okay, see you soon.